Everybody, it's Mr. Dan here. I want to give you guys, I just want to come talk to you guys about the homework that I assigned last week about the gas laws practice. There was a fair amount of, I don't know if it's confusion or just like some common errors with these problems, and so I wanted to come to you and go over it to see if I can clear up anything to help you out here. I also want to apologize. I know I made some mistakes on the questions that caused some confusion earlier on. And maybe with some of the answers too. I believe all those have been cleared up, so whatever score that you're going to receive should be accurate and fair. So let's just go through this. If you got it down, you know it well, go ahead and you don't have to watch, but when you watch this on YouTube, if you check down in the comments section, I'll try to put links to each one of these questions so that you can skip ahead and you don't have to listen to the whole thing. I'll also put this PowerPoint on Google Classroom so that you can just look at it that way as well. Either way, here I go. So just going to go through the questions linearly, one at a time, starting out with these questions about Boyle's Law. Okay, so here we go. So in reading this question, I'm not going to read it out loud to you, but in reading this question, we can see that that the variables that are present here, we've got volume in liters and we've got pressure in kilopascals, and those are the only two types of numbers at least that we're given. And so that's Boyle's law, pressure and volume relationship here. So first thing I want to do then is figure out what law I'm dealing with given the information that I've got, and then write out that gas law. From there, list off the variables that you're going to need to fill in, and then go back to the problem and input those in there. And so this is what we get here, right? Where P1 is 100 kilopascals, V1 is 2.29 liters, and P2 is 8.35 kilopascals. And we're asked to figure out what the final volume is of this. So here I've identified all the variables, and now I'm really ready to just put them into the equation. And so that's what I'll do next. And here's what it's going to look like. Okay, P1 times V1 equals P2 times V2, which is our unknown. So we've got to get this one here all by itself. So how are we going to do that? Well, some steps that we can take, because we have kilopascals on both sides of the equal sign, those are going to cancel out. And that'll leave us in our units of liters then, okay? And then we're going to divide both sides by 83.5, and that's going to isolate our variable of V2. So this is pretty simple to solve right here. So in doing that, on your calculator, you're going to get an answer of 2.7425. I asked you to round it to 0.01 decimal place, right, to 2 decimal places here. So that's going to be 2.74 liters for V2. Okay, next one. I'm not going to read it again, but in looking at the information here, look, I've got volume, pressure, and volume. So I'm looking at the relationship between pressure and volume. I've got two volumes here, which is a clue that it's going to be one of these, either Boyle's, Charles, Gay-Lussac's combined gas law, when you've got two different numbers for the same unit. Okay, so because this one is volume and pressure, again, that's Boyle's law, and go through and after reading it, figure out what numbers go in which place or which numbers are assigned to the correct variable. Once you figure that out, then you're just going to isolate for that variable, put it into the equation, okay, and then start solving for it. So here the liters, the volume is going to cancel out again, and we just want to divide both sides by 22.9 to get our answer, right? If we go divide by 22.9, right, then that's going to cancel, and then we take this whole side over here and divide by 22.9. Okay, and that's going to give us our answer. Okay, so go ahead and do that, right? Divide both sides by 22.9. Liters are going to cancel out, and so on our calculator we get this long number here. I asked you to round to 1 decimal place, so 96.9 liters is our answer for P2. Next one. Here, looking up here, we've got volume. Okay, so I'll put a V there, and I've got a temperature, and I've got another volume there. It's kind of hard to see, right? Okay, so I've got two volumes and a temperature. So that's Charles' law, where we're relating volume and temperature up here like this. So now that I've identified what law I'm going to work with, let's put the numbers into the variables so that we can then put it into our equation. I recommend assigning the numbers like this in advance before you start putting things into the equation, to just go one step at a time. It can be easy enough to put the wrong number into the wrong place. Like, for example, you could accidentally put 25 Celsius as T2 if you're not paying attention. Some of the problems are worded to trick you. Be careful of that. So I highly recommend assigning them like this before you get started. Now, you can't put them into your equation yet. One of the biggest problems I saw amongst all students was that many of you failed to convert the temperature from Celsius into Kelvin. So in order to do this, you just simply take the temperature in Celsius and you add Celsius plus 273 equals Kelvin. Okay? So anytime you've got Celsius temperature, you've got to convert it into Kelvin. Reason for this, you might run into a problem of having a temperature of 0 degrees Celsius. That comes up in a later problem, and you can't divide by 0. If temperature was 0 degrees Celsius here in Charles, you'd have an error on your calculator. So you can't do that. It also has to do with the way that the numbers are converted, because it's an addition thing. You can't use the same, you can't just put in Celsius. You can interchange different pressures because of the conversion factors that go into them. It's a multiplication. It's a rational thing. So you can just use kilopascals, atmospheres, millimeters of mercury, because you're multiplying by a conversion factor there, and you're doing these multiplication and division problems. But with temperature, because you're adding it, you can't just swap out Celsius. It doesn't work the same way. Okay, so once you convert this, now you're ready to put it into your equation. And so here it is. Here's what it looks like, right? V1, T1, V2, T2. And I've got to isolate for this V2 over here. So how's that going to look? Well, the temperature, Kelvin here, it's going to cancel out. Both of these are in the denominator, right? Here's the divisor sign. And they're both in the denominator, so we can just cancel those out. And then from there, you're just going to multiply both sides by 328. And by doing that, the 328 on the right cancel, and then we're going to put the number over here on this side. So multiply both sides by 328, and then just solve for it. So it'll be, I'll write it here for us. It's going to be 328. That looks hideous. Times 45 divided by 298. .53. That's 50 liters. Okay. Next one, still in Charles' law up here, but we can verify by identifying the numbers that we have, the measurements. Here we've got a volume in liters, a temperature in Celsius, and then another volume in liters. So volume and temperature, that's Charles' law. Oops, looks like I got I missed a slide. That's okay. And then I've already assigned those numbers into my variable slots here. But again, we've got Celsius, and so we need to convert that into Kelvin if we want to do our calculation. Now this one especially may be tricky because of the fact that we're asking for the temperature, the final temperature, to be in degrees Celsius. You might be tempted to just leave it that way, but you can't. Remember, like when we did the stoichiometry, everything had to get converted into moles to do the calculation. Similar here. It has to be converted into Kelvin to do the calculation. So we're going to do that, right? Convert that into Kelvin by adding 273 to the Celsius temperature. And now we're ready to put the numbers into our equation. So here we go. And we got to isolate for T2 over here. So there's a number of ways that you might do it. I'll show you one way here. I know I need to get this out of the denominator. I need to get it up top in the numerator. So I'm going to multiply both sides by T2. Okay, and that's going to get it out of the denominator here and put it over here on the left side even is what's going to happen. Okay, now I can shovel this. All has to go, these have to go over there. So how to do that? One phrase might be multiply by the reciprocal, if you know what that means. In long version, it looks like this. We're going to apply both sides by this number here, and we're going to divide both sides by this number here, okay? So what that looks like is we're going to multiply both sides by 548 Kelvin over 130 liters. Okay, that's the reciprocal of this here. So in doing that, right, in doing these two steps, that's going to isolate this by itself, and all of our numbers will be on the right side. Okay, so it's going to end up looking like that. Okay, 85 liters times then the reciprocal number there. Okay, next, the liters are going to cancel, right? Liters in the numerator and the denominator, leaving us with just our temperature in Kelvin. So plug that into your calculator. Oh, and then before we do that though, I don't think I put the number down here, but you're going to get a number there that's going to be in Kelvin. And so before you can move on, you're going to have to subtract 273 to that to get your final answer back in Celsius. Okay, so it looks like it's going to be about, well, if we put those two together, 358 is my guess, doing mental math there. 358 Kelvin, and then you're going to subtract 273, which is going to bring you back down to 85 Celsius. Okay, so you got to come back because that's what the question asked you to do. Okay, moving on then. The next question looks like we've got pressure. We've got two pressures here, and then we've got a temperature. So what's the law that's going to relate pressure and temperature? That's Gay-Lussac's law, written over here. P1 over T1 equals P2 over V2. Okay, so now I'm going to list out those unknowns and then find the numbers that go along with them. So I got to kind of read it. It says that it's going to go from 15 atmospheres to 16, right? It's going to go from here to there. So starting at 15 is going to be P1, and then P2 is going to be 16. It tells us the original temperature is 298, so that's T1. Oops, that one got synced up a little funny there. That's okay. A few typos I'll have to fix for next time. Okay, so now that I've got the numbers in there, put it into your equation. That's what it's going to look like. Okay, we need to get T2 by itself. Notice how this one is similar to the previous one, right, where we had T2 all by itself. And so we're going to do that again over here. Same way, multiply both sides by T2, and that's going to get it on this side, and then multiply by the reciprocal, or multiply by that number there, divide by this one here. So this is what it's going to end up looking like here, and from there we can just kind of put those numbers into our calculator. Our pressure units are going to cancel out, and we'll be left with our temperature, which is what we're looking for, right, in Kelvin. So put those numbers in. Going to get 317.866. Round it to the nearest whole number. So 318 Kelvin is T2. All right. Hang in there with me. You guys are doing good. All right, so next one. Here, let's take a look what numbers we've got. We've got a pressure, 3,000 millimeters of mercury inside a steel tank at 500 Celsius. And then we've got 0 Celsius. So we've got pressure and temperature again. So that's Gay-Lussac's. Looks like I've got some typos to fix over here. Put those numbers into our variables. Notice that we've also got Celsius. So we have to convert that into Kelvin. Okay, so this would be an example for why you cannot have 0 degrees Celsius, because when you put that number into this problem here, you're going to end up dividing by 0, which you just can't do. You're going to end up with an error in your calculator. So anyways, here we are. Here's the numbers. If you're not familiar with millimeters of mercury, by the way, this is how a barometer works, a classic barometer where there's mercury inside and it runs up a long skinny tube as the pressure increases. This is one of the first ways that we accurately measured pressure, atmospheric pressure, is through millimeters of mercury. I'll find you a picture or something. Anyhow, we've got our numbers here, so let's plug them into our equation. There it is, okay? And again, just solving for P2. Another error on Mr. Dan's part, that should be divided there, okay? So I'll go back and fix that on the presentation when I upload it into Google Classroom for you. Okay, so we got to get P2 by itself, so multiply both sides by 273, and in fact, here, let's, should we just do it right now? It should look like this. Okay, that looks a little bit better there. Let's go back to our presenter mode then. Okay, so now multiply both sides by 273, and that's going to get P2 all by itself, which is what we want. And as we go through here, look, our pressure, or sorry, our temperature is going to cancel out, leaving us only in pressure. So we can now just kind of put these numbers into our calculator. 3,000 times 273 divided by 773 is going to get us our answer in millimeters of mercury. So we get this long decimal. Please round to the nearest whole number. There you go. All right. Next, let's take a look at this one. We have pressure. We have 2 pressures. We have 2 temperatures. And we've got a volume. Okay, so pressure, temperature, and volume. And a couple of them at that. So that's going to fit into combined gas law up here. Here's the equation. It's all 3 of the others combined. It's Boyle's, it's Charles, and it's Gay-Lussac's all in one. This is a little bit more realistic situation for how gases will behave. So I've identified them all. Now we need to put those numbers into our equation over here. So there it is. It looks like we're going to end up solving for V1. All right. So here's how it's going to look. We need to isolate for V1, so there's a couple of ways we can do this. I recommend that since we've got this block of numbers over here, why don't you just simplify that by running the math, okay? So just reduce the left-hand side. That should be the right-hand side. Let's fix it. Let's fix it there, okay. So, back at it. Reduce the right side by just working the calculations. 1.2 times 48 divided by 320. And so that's going to look like this. It's going to equal 0.18. And then I left the units on here to help us track those. All right. Next, we need to get V1 by itself. So let's divide by both sides by this pressure and multiply both sides by this temperature. And that's going to get V1 all by itself. Now we can just sort of run this through our calculator. Notice how the units are going to cancel. Atmospheres on the numerator and denominator, temperature in the numerator and the denominator, and then we're left with just volume, which is what we want. Okay. So run those through, and this one works out perfectly. 117 liters is our volume, our starting volume. Okay. One more on combined gas law. So if we're doing combined gas law, there should be multiple pressure, temperature, and volumes up here. And here, look, volume, volume, pressure, pressure, and then we've got 1 temperature in Celsius. So put those into our list over here. Notice that it's Celsius, so we've got to convert that into Kelvin. It even gives us a clue about that here, answer in Kelvin. Okay, so put it into your equation. We're going to isolate for T2. So multiply both sides by T2. It's going to look like that there. And now we want to shovel these two numbers to the other, or all this to the other side. So there's a couple of steps here, right? Multiply by what's in the denominator, divide by what's in the numerator, do that to both sides, and so we'll end up with T2 equals this. We can clean up our units. Pressure and volume are going to cancel out because these are on the top and these are on the bottom of our ratio. And now our calculator can do the rest. Round to the nearest whole number, 160 Kelvin. All right, two left. Ideal gas law to finish things up. I think this one is maybe one of the more simple to actually work with, because you're always going to be missing just one. Right? On a straight ideal gas law problem, there will be just one variable that you don't have. So let's find out what that is. So here it's asking how many moles right off the bat. So that's N. Okay? We've got volume, we've got pressure, and we've got temperature. So have your list of variables over here. Once you see that you're working with moles, okay, ideal gas law is the only one that has anything to do with moles. And then it's also got the other four variables, or three variables. Okay, so this is what we've got here. These are our numbers. N is what we're looking for in moles. And let's put this into our equation now. PV equals nRT. So here it is. Now, take a look at this. Oh, there's another mistake by Mr. Dan. Better fix that so we don't get in trouble. Okay, so here it is in our equation. Pressure, volume, there's our moles. This is our R value, which is the ideal gas constant. Notice how it has all of the units present in there. And then this is our temperature here. The reason for this ideal gas constant, and here's the ideal gas constant for atmospheres, kilopascals, and millimeters of mercury, is that we need this to get rid of or cancel out all of these other units. If we didn't have the units attached here, right, if it just looked like this here, our final units would be kind of crazy. We'd have atmospheres and liters and moles and Kelvin all present. We don't want that, so this is going to help us get rid of all those. And this is actually derived from using the other gas laws. From Avogadro's principle to combined gas law, all this is present there. Okay, so that's what I think. So what we need to do is isolate for N, which is our moles. So you can see the steps. From there, this is what it's going to look like. So pressure times volume divided by R divided by R times T is going to equal N, or moles. So here's how it all cancels out. There's pressure, pressure, volume, volume, temperature, temperature, leaving us with just our answer in moles that's hidden in that constant there. So your calculator will do the rest of the work. Remember to round here to 1 decimal place. So this is going to come out to 9.9 moles. All right, one left, and then we'll be all done. Ideal gas law again. Okay, so this is describing a situation where the pressure is going to get very high and explode. Please don't try this at home. But ultimately, we're going to be looking for what is the pressure there. Okay, so that's going to be our unknown. Here we've got a volume. Here we've got our moles, our N, and here we've got a temperature in Celsius. So let's start putting that into our list over here. Excuse me. You can see temperature in Celsius, and so of course we want to convert that into Kelvin just by adding 273. Always do that. Don't forget. And then notice how for R I put it's up to you here because we're trying to solve for pressure. So this could really be anything. in your homework, if you solved this 4 kilopascals or millimeters of mercury, as I think about it right now, I know I did not give an answer in that. I just solved for it in atmospheres. So please send me a message if I need to go back and fix your question and give you some more points. I'd be happy to do that. Okay, so I said it's kind of up to you for which R value you're going to use. In this case, I used the value for atmospheres. And so I just put all this into my equation, and now I just want to isolate for this. So divide both sides by the volume, and that's going to be pretty simply get my P all by itself. Run it through my calculator after I cancel out all my units, and I'll be left with just atmospheres, which is what I want, and there's my answer, 275 atmospheres. If you want to see it in the other R values, I'll move my face over there. Here you can see using kilopascals, and so you end up with a different number here. And for millimeters of mercury, all 3 of these are the same amount of pressure. They're just using a different measuring system for it, but they're all the same. Okay, so you know, we can create conversion factors for these. Well, maybe that's for another video. So anyways, you guys, I hope you find this helpful. If you watch it all the way through, good for you. You're a champion. If you didn't, thanks for watching anyways. I'll try to send some more information to you guys soon. Let me know if you have any questions. Good luck, and thank you.